Hi folks, and welcome back to another exciting lecture in BCIT's Technology Teacher Education 4010 class. This is our Arduino programming class, and today we're going to be using TinkerCAD and using our Big Bad Breadboard board, and we are going to be studying some very exciting things. In the last few lessons, we've been taking a look at how to get information out of your Arduino, and we call those outputs. So our LEDs were outputs, and we use the digital write command to send information out to them. And then we hooked up our serial print commands, and we used a print command to send data to the computer down a serial data line. And then we hooked up our LCD screens, and we used a number of data lines, a parallel data port, to get data over to our LCD screen. So this has all been about getting data out from the Arduino, and those are what we call outputs. Today, we're going to take a look at some of the inputs. Now, before I go too much further into this, I know that a few people in the class have been having trouble getting their LCD screens to work properly. If you've got it working in TinkerCAD and you've gone over your wiring a couple of times and you've taken a good close look at it, you've watched for that potentiometer in there where we gave it a little bit of a bend on one leg. Um, Email me if you're not quite sure what I'm talking about with that. Then tell you what, bring it in next time you've got class with me on campus, and we'll find time to sit down and take a little bit of a look at it if you don't have it working just yet. Okay, but we are going to move on, and you are going to be able to move on and do this week's stuff, even if you're still having some problems with your LCD screen. Okay, we'll get it sorted out. No need to panic on that. The things that we're doing always work. They just don't always work the first time around. Okay, so today we're going to talk about our Arduino inputs. And the first command we're going to take a look at is the digital read command. And we're going to talk about these things called pull up and pull down resistors. And then we're going to talk about the analog read command. So we've done a digital write command and a digital read. We've done a digital write command and an analog write command. Now we're going to take a look at digital read and analog read. And we're going to come up with some terms in here. I'm going to talk about a 10-bit ADC, a little bit of jargon in here, and a bit of a refresher on our 8-bit PWM in the analog write command. So there's some little differences between analog read and analog write. We're going to talk about potentiometers. Well, we've been using a potentiometer to control the contrast on our LCD screen, but we'll take a little bit closer look at what they are and how they work. And then we're going to go and dig out a light dependent resistor and use that to talk about voltage dividers and how we can read them with the analog write command. Sometimes the light dependent resistors are also called photoresistors. Now, if you're not quite ready to jump into all that just yet, you can go and get some parts. And so here's a few of the parts that you're going to want to get. This is a potentiometer right here, or this is the potentiometer that we're going to be using. And I probably gave that to you the last time you were on campus for one of our labs. This is a push button switch, a momentary push button switch. Has a very satisfying click sound, and you would have got that back from me in first semester when I gave you your Big Bad Breadboard kit. Now, I can't remember whether I gave you one or two or whether we soldered them into a circuit somewhere. If you've still got one, that's great. If not, you might have its little brother or little sister over here. It's got pins on it. Little brother. Um, you might have its little brother over here. Um, and we can make that work too. It just doesn't stick into the breadboard quite as permanently as the bigger one. And what else are you going to use on here? Also in your Big Bad Breadboard kit, if you dig around in there, you will find a light dependent resistor, also known as a photoresistor, that you'll be able to identify because it has this lovely zigzag pattern on its face. It's nice and shiny right there. There we go. You can see that lovely zigzag pattern all set up for changing how much resistance you get depending on how much light is landing on it. So interesting stuff that we've got going on right in here. And you don't need to grab it right now, But those are the things that we are going to be working with a little later on today. Okay, as with past lessons, we're going to start this out in TinkerCAD because if you don't happen to have one of the parts, there's virtual parts in TinkerCAD that behave a lot like the real thing. So let's go ahead and log into TinkerCAD here. And while you're logging into TinkerCAD, I'm going to turn that screen off and remember to hit the transition button. So here we go. We're over in TinkerCAD right now. And the last time we were in TinkerCAD, your code probably looked something like this, and your board looked something like this. We've got the LCD hooked up and running on here, and that's good. That's great if you've got that. What you can actually do is you can change the name of that if you want to keep different copies, and you can save it again. You can make copies of it back when you're at your directory. It's all good. It's all virtual, so it's not a big deal if you end up losing something. Let's start by talking about the digital read command. Now, you can do a digital read with any of the pins on your Arduino, okay? And let's move the code off to the side here so we're not looking at code. Let's just take a look at our components here. And I always instinctively just tell it that I want, oh, yeah, it'd probably help if I shrunk myself down here. Gonna move off to a different corner of the screen. Hello, down here now. Um, yeah, so I almost always go from, instead of just looking at the basic components, I'll take a look at all components just because I like knowing what's on there to play with. And the thing that we're going to start off with is a push button switch. Now there's different types of switches, obviously, because there's lots of different types of switches out there in the world. And we're just going to drag that push button onto here, and it's not quite as big as the ones that we've got in our kit. So I'm going to put it right here, but as you saw in our kit, um, we had it going right across the middle right here. So it came in on that side. Now, the push button switch is pretty cool. You've got terminal 1A and terminal 2A over here. And when you push that button down, it connects terminal 1A to terminal 2A. The symbol for this type of switch, and there's a few different types of switches that we can use like this. Let me just turn on the camera right here. And so we're using what we call a momentary push button. Normally open single pole, single throw switch. Okay, you thought we were just using a switch, but there's a little bit more to it than that. Okay, and the symbol for our switch, if you were looking at it in a schematic drawing, would be something like this. The wire would come in right here. And then there'd be this hat looking thing, and you can recognize that as a button. And so when that gets pushed down, what it's indicating, oh, that, just ignore that. That arrow is not part of the schematic. That's just me saying that you're going to push that button down right there. And when you push that button down, this connects here, and electricity can go through the switch. Okay, so that's all really good. You might also see a switch that's a slide switch or a toggle or another way to draw a single pole, single throw switch would look something like that. But this is usually a toggle type switch that will stay open and closed when you throw the switch, whereas this one tends to be momentary. Now, what we mean by normally open is that when you're not pushing the switch down, there's no connection between these two. It's also possible, I'll mark that as NO, it's also possible to have an NC switch, and that will typically be drawn like this. Okay. And the normally closed switch, as you can see when it's in its rest position, is connected right here. And when you put force coming down on here, that breaks the connection. So when you push this one, it closes and makes the connection. When you push this one, it opens and breaks the connection. So this one is normally open. You have to push it to close it. This one is normally closed. You have to push it to open it. Um, you don't have any of these in your kit. I didn't give you any of them just because I don't want to mess things up for you. But yeah, you can forget about that largely. But just know if you ever see an O on there, that it doesn't mean that it's a no switch. It means normally open. The single pole, single throw means that you can only throw it in one position. Okay, so the single throw means that you can close that like that. If you had a double pole switch, you'd be able to swing it from one position to another right on there. Double throw switch, two different positions that you could throw it to. And if you had multiple poles, that's like sort of having multiple switches in parallel. So we'll come back to this terminology and we'll talk about the DP, DTs and DP, STs and SP, DTs, and all of those things later on. Don't worry too much about them for right now. Just know that those are terms that are coming along. And if we talk about them 3 or 4 times, they'll start to settle down in the back of your brain and eventually they'll make sense. Okay, so we've got that switch. And again, the one we're using in the real world is a little bit bigger than that, but we also have the little one right here that you're using in TinkerCAD. And when you press them, they have a very pleasing click, and probably a very pleasing click that reminds you of playing some video games, because quite often you have a controller that's got a plastic button that pushes down on one of those little momentary switches. Sometimes you'll see those little ones referred to as a tactile switch in the electronic shops. But okay, back to TinkerCAD. Enough of this reality. So we've got this switch tucked away right in here. And what we want to do is we want to be able to read what's happening with that switch. So what we're going to do is we are going to connect a wire. Let's use digital pin 8 and draw that out right to this lead right there. And let's see, I'm using a yellow wire on my board. Let's make that yellow right in there. And now you can come along. And if you want, you can put a nice little kink in the middle of it so it comes up there. Good. Okay, so now pin 8 is going to read right here. And then on this side, we're just going to take that and connect it into ground and give it a nice black wire because that is connected to ground. So there you go. You can see we've got our switch in here and pin 8 is sitting right here, and this comes down to ground right here. Alrighty. Now we're going to do one more little thing right here. And in fact, I really wish I could have just moved that up there. We're running out of holes to stuff things into. We need to add a resistor to this, and I'll talk about why we need a resistor in just a moment. But the resistor is going to come right in there. Now, virtually, it's going to let us stuff that resistor right in there. Okay, don't go trying to stuff two things into one hole. In the real world, it doesn't fit nearly as well, but I think TinkerCAD's going to let us get away with it. So that resistor is going from our positive line right here in here, meaning that unless the switch is closed, we're always going to be positive right here. And then when we close the switch, the electricity is going to flow down here. This point is going to become 0 volts. So let's take a look at what we would do with this right here by writing some code. Now, I know a lot of people still have some fondness for the blocks, so let's do blocks plus text. We're going to lose all our LCD code. Don't worry, it's still in there somewhere. We'll continue on right here. Brilliant. Okay, then get rid of that basic code that it gives us right there. Now, what we're going to do right on here is we are going to get an input, and we are going to read the digital pin number 8 right there. So digital 8 D8, okay, and you can see the commands that it pops up right in here, okay. Now, this isn't going to do anything for us. I mean, it's going to go around and it's going to read the digital pin 8, but we're not telling it to do anything. So what we're going to say in here is we need some control, okay? And in our control, okay, we've got an if statement. So we can bring this in right here. We can say if a condition is true. And then we can come to our math, and you'll see that we've got those little triangular ends. We're looking for something triangular to put right in here. And we can say if, and now we've got rounded ends right here. If we read digital pin 8, okay, and it is equal to 1, okay, then we're going to do something. Let's do some output right here, and then we are going to digital write, set pin. Let's turn pin 9 right here, because 9 we've got hooked up to an LED. And if you don't have it hooked up to an LED, well, there you go. That's go ahead and hook it up to an LED. And we'll set that to high. Now, this is one of those cases of our code doing what we tell it to do. Well, let's see what happens if we run this. Okay, it's running. The LED's on. I come over here and I push the button, and the LED's not going off. You can actually just take your mouse right down here. It's pretty cool, and just click on that button. But the LED on pin 9 stays on. Well, why does it stay on? Because we never told it to turn off. This is a classic case of the computer doing what we tell it to, not what we want it to. So you have to think through and really tell it clearly what you want it to do, because if you don't tell it what to do, it won't do it. So if the digital pin right here that we're reading, if this pin is high, okay, in other words, if it's equal to 1, then we're going to set this pin high. But if it's not, we need to do something different. Let's come back and take a look at our controls, and you'll see in our controls we have an if, then, and an else statement. Let's just take some of our commands right out of here and drag them. There's our condition comes in here. Get rid of that if statement. Okay, and now we'll set our output right here. And so if digital 1 is high, we will set pin 9 to high, and otherwise we'll set pin 9 to low. Now, following, and this is what I like about the blocks and text, and while I always say to use the blocks plus text statement, because it takes us through our setup routine, and you can see that it gives us some pin modes, and in this case, it set pin mode 8 as an input, and it set pin mode 9 as an output, because we're going to use that to control the LED. So that was when you drag those blocks in, it did that for you automatically. And now here you can see, here's the if digital read 8 statement. Now, interesting to note, on here you just see a single equals. But when you go to do it with text, it's really important that you use the double equals. Yes. It's one of the little frustrating things when you switch over to the text, is that there's a difference between a single equal, which is an assignment or a command, and a double equal, which is a question. Okay, so what we're saying in here, do this, read digital pin 8, and then I have a question for you. Does it equal 1? Okay, now 1 is our logical symbol for high. Okay, so we're saying, is digital read pin 8 high? Question mark. and the question mark is represented by the two equals. If you only had one equal in there, what your command would be saying is make digital read 8 equal to 1. That's something that the Arduino can't really do. Okay, it would try to do it and it would execute the command because it's a logically correct command, but it would fail, nothing would happen, and nothing useful would happen. So if you're running into problems and your if statements aren't working properly, watch for the double equals right in there. Now, here's our squiggly brackets again, our ellipses, and you'll see that this ellipses matches up with this one right down here. And what that means is that everything between this point and this point, that's like that orange hug right in here, okay? Everything in that orange hug is controlled by this if statement. And here's two more sets of ellipses, and everything inside them, just like down here, our else statement wraps this up. Everything between those is controlled by the else statement. And then we come to our delay, and here's a couple more ellipses. Well, these are for our void loop, and that just means this keeps on looping around and around and around forever. Okay, so it's coming in here, it's going to read that, and let's start the simulation and see what happens. It's running, our LED is on, we push the button, the LED goes out, we let the button up, it comes back on. Now, I know you're sitting there and you're saying, well, Jason, this is thrilling. You've just figured out the light switch. Now, we could definitely have just hooked that little button up in line with the LED, and when we push the button, the LED would come on, and we let it go, it would go out. There's all sorts of different ways we could hook this up without using a microcontroller. But what we're interested in is, can we get that data into the microcontroller? We could have all sorts of other things happening in here. We could have it send a message to the serial print. We could have it send a message out to the LCD. We could have it start a motor or all sorts of things like that. We've just chosen to turn on an LED because it's pretty quick and easy to do and easy to see. Alrighty, now there's some interesting things happening in here, and specifically about what high and low means right here and how we're reading that. So let's just take a look at, I'm just going to stop the simulation right here, and let's close our code window for a moment. And in your components right in here, you've got a multimeter somewhere down here at the bottom. Okay. There we go. You've got a multimeter. So you can drag a multimeter in here, and we can plop it right in there. And we're going to measure the voltage at this point right here. May as well set that to yellow just to keep it. Oh, actually, I want that going to the red pin over there. Okay, the red is our positive pin, so we'd use our positive test lead there. And our negative black lead is just going to come right down here. We're going to get rid of this in just a moment, so it's okay that it's a little bit ugly. Okay, let's start that simulation and run it. And right now you can see that comes up to 5 volts. But when I push the button, and really it switches instantly. The simulator just takes a little bit of time because it has to do its math. It switches back and forth from 5 volts down to 0 volts. Well, just want to take a look at what's going on right in there electrically, because that's what our digital read command is reading. It's reading that digital transition. And so let's take a look at how that looks on a schematic. So on our schematic, what we've got is we've got our push button switch right here, momentary, normally open push button switch. Now on one side of that switch, coming off of our +5 line, we have a resistor right here, and we've got +5 volts right here. And on this side, we connect into ground. And our Arduino pin comes in and reads right here, and that goes off to the Arduino. Now, this resistor is really important because if that resistor wasn't there and we just had this as a circuit, when the switch wasn't pushed, this pin right here that we're reading wouldn't know what voltage it was supposed to be at. Now, I know that's a bit of a personification. Pins don't know what voltage they're supposed to be at. That's not how things work, but it's a fair statement. This is what we call a floating pin. It's disconnected from anything else. And so stray random electromagnetic fields traveling through the air could come in here and induce a tiny little current on here, and that could change the status of this pin. Now, when you push that button down, it's always going to be ground. But we put this resistor on here, and this resistor is called a pull-up resistor because right now you're hooked up to +5, and when you're hooked onto there, that means that this line is forced to be at 5 volts. There's nowhere else for the electricity to go until this button gets pushed down, and then the electricity can come down here and go to ground, and you'll have a closed connection right here. This pin line will be directly connected to ground, and you'll have a big voltage drop, a 5-volt drop right across the resistor, and all will be good. You'll see 0 volts going into the Arduino just as we saw. So this is what we call a pull up resistor. Okay, now it's also possible, you can have a pull-up resistor, that you might have a pull-down resistor. And if you had a pull-down resistor, you'd have your +5 here, and your pin right here, and right here. And the pull-down resistor would be on this side, and your Arduino would connect in on that. So what this would do is that until the button gets pressed, the pull down resistor takes care of any spare or weird or unexpected currents that might be induced into the wire, takes them right down to 0 volts, and this pin is pulled down to 0 until this button is pressed, at which point the +5 volts flows straight through here, and you've got a 5-volt drop across the resistor, and your Arduino sees the full 5 volts. Now, what voltage does the Arduino need to see in order to determine between high and low? Generally, if you're somewhere between 0 to 2 volts, that's going to be interpreted as low. And if you're somewhere between 3 to 5 volts, that's going to be interpreted as high. And if you're somewhere between 2 to 3 volts, well, it'll probably switch at around 2.5 volts between high and low, but don't gamble with it. Make sure that you pull your pins nice and low or pull them nice and high, just like we've seen right here. Now, because the pull up resistor and the pull down resistor is so common and such a useful thing to have when you're reading switches, the people that designed the Arduino did make life just a little bit easier for you. Since this line right here is hooked up back to the Arduino, they said, well, why don't we take it so that the person setting it up doesn't have to put a pull-up resistor in right there. We'll come back to the Arduino and we'll put a pull-up resistor right inside the Arduino right over here. So that line can be pulled up automatically. And that's what we call an internal pull-up resistor. And you can use an internal pull-up resistor on the Arduino by configuring it so. So let me show you what that looks like. I think we can do it in TinkerCAD. Let me switch the screen over. Okay, right here. So this right here is our pull up resistor because it's connected into +5 on the side and it's pulling this pin up high. Just going to get rid of that. Oh, I need to just stop the simulation, I guess. Something's going on here. Start simulation, stop simulation, resistor. Resistor. That resistor doesn't want to go anywhere. Half a second. Okay, that's really weird. The only way I can get this resistor to delete is by deleting the yellow wires first. Now I have to go back and put the yellow wires back in, make them nice and yellow again. There we go. Now we've got our wires in right here. And if I start the simulation, now you can see when that's running, there's no voltage. It's just showing me nothing coming to that pin right there. Okay, I push the button and it takes it down to ground. That's because we're lacking a pull-up resistor. Now let's bring our code over right here and let's see if we can do anything with our code right here. I want to change this command from input to say input pull-up. And I don't think the drag and drop function has that available for us. So what I'm going to do is I am going to switch my code from, I'm going to stop that simulation, and I'm just going to go over to text. And I'm going to lose all the blocks, but I should keep all the code. All right, so now I've kept the code, and now we're typing code into the computer. And we can edit it manually. And so if we don't want to put a real genuine pull-up resistor onto the board, we can say input, and then we go underscore and pull up, all in capitals. And what that does is inside the Arduino chip, it comes along and it turns on its own internal pull-up resistor. Okay, there's no such thing as an output pull-up resistor because you're actually controlling what's on the outside of the Arduino. You're setting things high or low, but when you're reading things, the switch is so common and the need for a pull-up or pull-down resistor is so common that they've built a pull-up resistor into the Arduino. They didn't build a pull-down resistor. Guess they figured it was easier to make the pull-up. All right, if we start the simulation now you'll see that this pin automatically goes up to plus 5 volts because the Arduino is supplying a very tiny little bit of current right there to set it high. And now we can turn it on and off again by clicking on it. So, so that's your digital read command and your momentary push button switch. And yeah, pull up, pull down resistors. It's kind of cool. Now, in the event that you are ever stuck somewhere without a switch and you need something that's going to work like a switch, don't panic. Okay, let's stop the simulation. And if I didn't have a switch right there, I could delete that and just go ahead and use a big fancy piece of wire. I'll make that turquoise because that's a nice color. And if I start the simulation right here, you can see that oh, it would work better if I put it into the right hole. To simulate that switch, put it into that hole right there. And now with the wire plugged in, that's just like closing that switch right there. It's like pushing this down on the switch, and we're at 0 volts on this pin, so we've got no light coming out the LED. And if I want to adjust my wiring, I stop the simulation and I unplug that wire. You just go somewhere else. We delete that wire and we start the simulation. You just unplug it in the real world. TinkerCAD's giving me a little bit of grief right there. So, and now it's up at 5 volts and the LED comes on. Okay, I'm going to stop that simulation and disconnect this lead. right in here. But I'm going to leave that potential that multimeter right on the board. I just might move it over here for right now because we'll probably use it again, because now we're going to talk about a potentiometer. Okay, so the potentiometer is pretty cool because instead of it being a digital read, which is either on or off, this is an analog read. And just as our digital write was either on or off, and our analog write let us control the brightness of something so we could have it be a little bit on, our analog read is going to be able to check things that are a little bit on. So let's get the code off the screen right here and take a look in here, and we should be able to find some potentiometers. And where's a potentiometer in here? So we've got resistors, and another word for potentiometer is a variable resistor. So here we go, we've got a potentiometer right in here. Do they have anything else? Sometimes they have different looking potentiometers. There's lots of different looking potentiometers out there in the world. And let's just drag this one in, and we'll put it right over here somewhere. Okay, now last time when we used a potentiometer, you can see we tucked a few wires around in the back of it so that we could get red and black coming off the potentiometer. So let's do that again right here. And we're going to set this side into the plus 5-volt line and this side into the ground line. All right, then we bring our potentiometer and hook it up right here so you can see it's going to have that line is going to be red and that line is going to be black. There we go. We'll just set it right there. And now what we're going to do is we're going to run a wire from here all the way down. Oh, I'm making this horrible, ugly wire. It's going to go into A1 right now and put it in right there. Bend that around. Let me just move this board up so I can route this poor wire a little more neatly. There we go. That was more what I had in mind. Keep our wires nice and neat, makes it easier to track the board and what we're doing a little bit later on. Okay, so our potentiometer is a pretty cool device. And I'm just going to stop and explain what the potentiometer is doing for a little bit before we start using it and start talking about the analogRead command. So let's switch back over here. And inside your potentiometer, you've got some pretty cool stuff happening. Now, potentiometers come in different sizes and shapes, and this is one that I would have handed out in class a little while back. This is designed to go into a printed circuit board and sit there like that, so you can just dial things right on the printed circuit board. That's why it's got these two mechanical clips. These don't actually do very much electrically. They're just there for holding it in place. And then we've got our 3 pins right here. And those 3 pins, when you get them, aren't going to be splayed out like that. You're going to have to just give them a little bit of a twist. Be gentle, try not to snap them. And you want to do that so that those will plug in to your printed circuit board, or to your big bad breadboard board, into the breadboard. Okay, and so you can go ahead and plug those around. Now there's other types of potentiometers. Here's a potentiometer right here, and you can see somebody's just soldered some wire in there so they could fit that into their breadboard, and they did a nice job of braiding it. And here's another one that's been braided to go in there. And this is a potentiometer as well. And they come in all sorts of sizes and shapes, just like the one that you've got hooked up, controlling the contrast on your LCD. Now, one of the things that you will see on a lot of potentiometers is right here, you'll see where it says B50K. And most of the potentiometers you're going to see in our shop will begin with the letter B. The letter B means it's a linear potentiometer. And linear means that if I turn it halfway up, I'm at halfway to the maximum resistance. And if I turn it 3/4 of the way up, I'm 3/4 of the way to the maximum resistance. Basically, it's a linear straight line slope. If you turn it 10% of the way up, your resistance is 10% of the way up. That's in comparison to an audio taper or logarithmic taper potentiometer that are used in specific applications, as you might guess by the name, audio. Because in audio, if you're going to increase the apparent sound volume of something, you can't do it on a linear basis because our ears don't pick the sound up that way and the energy doesn't travel that way. So um, if you see one that says A 50K, then you're dealing with an audio taper, and it'll work, but maybe not so well. We're looking for ones that say B on them. And the next number that you see on there is the maximum resistance. So this is a B50K. So you've got 50K ohms of resistance between the two outside holes right there. So we've got 3 holes on every potentiometer, or 3 pads, 3 pins, 3 connections, whatever you want to call them. And the 2 outside ones are the ones that are separated by a 50K resistor. On this one, it says B100K, so it's a linear taper pot, typical ones that we'd use, and then it's 100K between here and there. Now, the middle one is where it gets interesting. This one, let's just say, this one only says 10K. It doesn't tell you what type of taper it is. Looks like they saved 1 character's worth of printing. And this one is designed for being adjusted with a screwdriver. So you'll see that there's a little screw setting right in there, and you can just turn that back and forth. And this is what we'd call a trimmer pot, because if you're trimming something or adjusting something once at the factory and you want to set it right there, you get it dialed in so it's working perfectly. You put a little dab of glue on there, and then your equipment's all trimmed up and ready to go. The pot you're going to be working with should say B10K right on the back of it. Come on, camera, focus. Okay, it's focused in there somewhere. There we go. B10K. So what you've got is you've got 10K ohms of resistance between here and here. Now, that 10K ohm of resistance usually comes in the form of a little disc of carbon. And so when you're looking at the a potentiometer, what you actually see is a little bit of a horseshoe shape, something like this, of resistive material in there. Okay, so in our case, this resistive material is going to have 10K ohms of resistance between right here and right here. And if you only ever use those two, that would work perfectly fine as a 10K ohm resistor. But in the middle of it, there's a dial that you turn either with your fingers or with a screwdriver, and there is a lever arm, a sweeper, that's attached to that dial right there, and that comes out right like so. And as you turn the dial, that sweeps back and forth across the potentiometer, and this is what the middle pin is connected to right here. Okay, so as I turn it this way, this gets quite a bit closer to over here. So you can picture it that this splits this one big resistor into 2 smaller resistors. And where it's positioned controls the size of each resistor. So right in here, I've got a small resistor, and right across over here, I've got a big long resistor. So electrically right now, in this position, this pin is closer to this pin than it is to that pin. When it's perfectly up and down, it's halfway in between. Now, that's useful for lot of things. So if you want 5K of resistance between this side and 5K between that side and that side, you're great. If you want 10, what would be at about 3K and 7K over here, that works out as well. And you'll see when we talk about voltage dividers, that makes a lot of sense that it's doing that. But what we're going to do with it is you'll remember that we hooked this side up to plus 5 volts, and we hooked this side up to ground, or 0 volts. And when we sweep that potentiometer back and forth in right here, at the very middle, well, we're going to be halfway between 5 volts and ground. And if you're to come down to this side, you would be at the full plus 5 volts. And somewhere up in here, you'd be at 3 volts, because we're starting at plus 5 and we're coming down. And somewhere in here, you're going to be at about 4 volts. Over here, you'll be at about 2 volts, 1 volt, and of course down here, your output will be at 0 volts or ground, because you'll be connected right in here to the same place that this line is connected. So your potentiometer, as you sweep it back and forth, if you've got it hooked up with one side at plus 5 and the other side at 0, can give you a varying voltage output. And so this voltage is going to be somewhere between 0 to 5 volts. And that's going to go back to our Arduino, and that's going to go to the 10-bit ADC, or analog to digital converter. So for something with a very techy sounding name, a 10-bit ADC, it's actually pretty simple. It's an analog to digital converter. It's a voltmeter. It reads the voltage and it turns it into a number. How many binary numbers does it use? Well, just like our analog write command used 8 bits, this is going to use 10 bits. So that means that the numbers that it's going to see range from 0, 0, 0, 0, 0, 0, 0, 0. How many? 1, 2, 3, 4, 5, 6, 7, 8, 0, 0. So this is slightly more than a byte, okay? This is a byte right in here. Remember, our byte is 8 bits, but if you put zeros into all the bits, it still equals 0. And the biggest number that we're going to see on here is 1, 1, 1, 1, 1, 1, 1, 1. Now, you'll remember that if you have a byte, the biggest number that you can see is 255, because this is our 1s column, our 2s column, our 4s column, our 8s, our 16s, our 32s, our 64s, and our 128s. So if we've got 1 byte filled all the way up, add all that up and you get 255. But this is 10 bits, so we have the 256-bit column out here and the 512 right out here. And you'll notice I didn't memorize the sequence. I started at 1 and I just kept doubling it. Okay, you go through the entire progression of Nintendo game consoles in the middle. So when we add all that up, we get a maximum value of 1023. Okay, or 4 times what you'd get with just 1 byte. So we got 4 times the precision that you can fit into 1 byte of data. So it's going to have to use 2 bytes of data to store this. Or what you can do is you can simply divide by 4 and it shifts all the bits over that way, and you lose the ones at the end if you don't need that much precision. But in any case, you've got 1023 possible combinations, which means that when you're reading this, that when we're at plus 5 volts, you're actually going to read not plus 5, but you're going to read 1, 0, 2, 3. And when you're reading 0 volts, well, you'll read 0. And when you're right smack in the middle, you'll read 512. Now, someone out there is doing the math and they're saying, ho, 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 no, you wouldn't. You'd be reading 511.3 because that's 0.5 because that's half of 1023. Remember that we're dealing with integers here when we're talking binary numbers. It's okay to round off. You kind of have to. So that would be at 512. Basically, if you take your 1023 and divide by the 5 volts that the Arduino is running at, you'll get a number that comes out to be 200 and almost 205. If it was 1025, it would be 205, somewhere around 204 to 205. I guess 205. So basically, 200, move that up, 1023 divided by 5 gives you roughly 205 readings per volt. So 1 volt is going to be about 205. 2 volts is going to be 410. 2.5 will be your 512 in there. 3 volts will be 615. 4 volts will be 820. And your full on 5 volts will be 1023. So if you ever want to know the exact voltage that you're reading, just do an analog read and divide by 205. Okay, you don't have to do all that, but you'll see how that works when we go back to TinkerCAD here in just a moment. Let's see. Okay, so we've got our potentiometer installed in TinkerCAD right here, and you can come in here, and when the simulation's running, you can spin the dial. We can't do it right now because the wiring's, it still thinks we're setting up wiring. But let's come over here and take a look at our code. Now, you can save this code, make a copy and paste of it, hang on to it. The main reason we got away from the blocks was because we wanted to do the input pull-up. Let's go back to blocks plus text because that takes care of so many typos. And in the process, we lose all that code. Not a great loss. Okay, so what we want to do right now is we want to read our potentiometer. So what we're going to do is we are going to come in here and we're going to send this data out to the serial monitor. Okay, now we don't want to read hello world out there. What we're going to do is we're going to do an input and we're going to read an analog pin. And there's a 0 right there. We're actually on analog pin 1. Now you'll notice that we're using these analog pins right down here and that they're named A0 through A5, and there's only 5 pins on the Arduino that can actually read the analog data. Okay, so if you tried to do an analog read over here, it just wouldn't work because they didn't build the hardware for it into the chip. These are special pins on the Arduino because they have that 10-bit ADC. Alrighty, now over here, you'll see our command coming along right in here, and it says serial.println, so that is with the line carriage return, and then it does an analog read on A1. It'll print that data out. Let's just add a little bit of a delay in here so that we're not, well, we'll leave it at that. Let's just run it. Okay, the simulation's running, and now we need to bring up our serial monitor. And there's your serial monitor button down at the bottom of the screen. And you can see right here, it's flashing away and telling us 1023, 1023, 1023. And that's because our potentiometer is turned all the way up. If you start turning the potentiometer down, there we are, we're at about halfway. Just click and drag that face, 511. That's close enough to halfway for me. Satisfy all those people who said, told you it was going to be 511 and a half. And then we come down all the way, and now we're reading 0. So we're at 0 volts right here. If I turn it up to 205, okay, that means that I'm about 1/5 of the way from ground up to 5 volts, and I should be getting 1 volt coming in on that pin right there. Let's take a look at that. Just stop the simulation for a second and move that code off the screen so we can see what's going on. Take your multimeter right there, bring it over here and plug it in and start your simulation again. There we are. When that's running, we're at exactly 1 volt, 1000 millivolts. And if we bring our code in right here, you can see it's reading 205. Okay, if I turn it up to the halfway point, I'm at 2.5 volts right there. Okay, is it going to be 512 or 511? Oh, the 511 people win. Okay, and we'll stop that simulation right in there. Now, what can we do with this code? Well, right now we're printing that data out to the serial monitor, but we could bring another command in here and we could make an output. And so we did use an output to print it out to the serial monitor, but you could also tell it that we're going to set pin. Let's use pin 10 this time because we've got an LED still hooked up right in there. And then it says, well, set pin 10 to what? So now let's come in here and let's come to an input, read analog pin A1. Okay, and now just as for our serial print command, we come in here and we read the analog command and then we write it out directly to pin 10. So it's kind of neat. We've got these commands stacked in here. So this command right here, follow all the brackets, is just like math. You come to the inside most brackets first to find out what's going on. And it says, okay, we've got A1. We're passing A1 to the analog read command. And the analog read command is going to go out and take that A1. It's going to go take a look at pin A1. It does its analog read. It comes back with a number. And then it says, right, I'm going to pass that number over to the analog write command along with pin 10. And I'm going to write that number into pin 10. And let's see what we get when we run that. So let's start our simulation right here. And I'm going to move the code off the screen here for just a second. Spin this dial. And gets dim. Now notice it gets bright again. Now because we're running this on the simulation, it's a little bit time laggy compared to what you'll see in real life. But I'm dark. I come up, get brighter, brighter. Let's go slowly around here. Notice it got dim right in there again. Went from full bright to full dim right around 1.3 volts. Then we come all the way up here, it gets brighter and brighter and brighter, and right at about 2.5 volts, gets dim again. Then it comes in here, and then it gets dim again, and then it gets full brightness by the time we get back down over to that side. Brighten and darken 4 times in the middle. What the heck's going on in there? Well, you might have some ideas already. Let's take a look at our code and let's take a look at what numbers we're reading right in here. Let's bring it back down to this side. So at 0, everything's off because it's analog rate 0. That makes perfect sense. We come up here, 102, it's getting brighter, it's getting brighter. Somewhere right in here, 225, 245, it just got dim again. Where is it at its dimmest? Just move that back and forth. 266, that's about as fine as I can get. What happened? When I was at 245, it was really bright. But when I got to 266, it was really dim. Now, what's the difference between 245 and 266? Feel free to press pause and ponder that for a second, because I'm going to switch this screen back over here. Remember I was talking about binary numbers and how when we get to 255 with our byte absolutely full up, if we go to 256, the way that 256 is expressed is a 1 in the 256 column and zeros in all these columns. Now, when we read our number, we're reading in 10-bit ADC because that's what the analog digital converter can read. But when we do our pulse width modulated analog write command, we can only write 8 bits of data to it because that's the way the PWM command's set up. We've got more precision in our analog read command. So what's happening here is we're coming along right here and we're getting up to 255, all perfectly good. And as soon as we hit 256, well, this bit turns on right here, but all these other bits turn over to 0. And our analog write command just sees the zeros. So that's why it goes dim all of a sudden in there. So, and that's why you'll notice it happens 4 times as we go around. So let's see what we can do about that. Come on over here and maybe add a little math command right in here. And what we want to do is we want to write, bring this down here, just take this number out right in there, put it right in there, and change that to a divided by 4. And then pop that in right there. And now we're going to do our analog read, divide it by 4. You'll see that there's brackets around there because that means that we're doing that first, just like with all your algebra. And so let's go ahead and run this simulation now. And now we bring it all the way down. It's very dim, brighter, 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 all the way around with no bouncing around. And we get our brightest at the top side because we do that divide by 4. So we're mapping our 1024, our 10-bit number, onto a smaller 8-bit number by dividing it by 4. And in binary math, that just dividing by 4 just consists of shifting all the bits over this way a little bit and throwing the least significant 2 bits off the end. Now, this gets kind of cool because we can use things other than the potentiometer as well. So I'm going to stop this simulation and get my code off the screen right here. And as I was saying, we've got a photoresistor or light dependent resistor. And I'm going to bring that in and drop it in right here. Okay. And now to make that work, we are going to have to pair it up with another resistor because otherwise we wouldn't be able to read too much off of it. I'll explain a little bit more about that in just a moment. So bring a resistor in here and pop that resistor in and we'll run the resistor right in there. Let's just make sure that goes on top right there. And then we'll run a wire from there back to ground and make it nice and black. And then off this side where the 2 resistors meet, let's come down here and run a gray wire. The electrons really don't care what color the wire is. Just I happen to have gray already set up on my breadboard, so we can hook it up that way. Alrighty, so that's hooked up in right there. And now we're going to do our analog read, but we're going to do our analog read on pin A0. So let's bring our code back over here and let's just read and output the data from A0. So we're just going to take a look at that data. We're just going to leave the potentiometer over here, spinning that LED on and off, whatever. We'll do something kind of fun with that in just a moment. But let's go ahead and start the simulation. And now we've got a number running right here, and it's reading 1017. Now, if you come over to your light dependent resistor, you can start adding light to it. And as it gets brighter, you see that number goes down. And as it gets darker, see the black dot for dark and the bright sunny thing for bright, we can control that back and forth. Obviously, it's not going to work if you take a bright light and shine it at the screen. There's no input on the screen for you to read, so we simulate it by sliding this back and forth. But in the real world, actually putting your finger over top of it makes it dark, and putting your cell phone's flashlight over top of it makes it go bright, and exposing it to bright sunlight makes it really, really bright. And you can see right on here that we're seeing a range of values from 1017 going all the way down to 344. And that's because we've paired it up with a 1K ohm resistor. Now, if you change that 1K ohm resistor, I don't know if it's going to let me do that to a 10K ohm resistor right here. Okay, some of those numbers are going to change because what we're looking at is something called a voltage divider. And now you see we go down to 44, but only up to 969. Let's take a moment to talk about why that's happening right in there. I'm going to stop the simulation here. No sense making the computer do too much work. Turn my screen back on over here. And when I talk about a voltage divider, it's nothing too fancy. What we've got going on right here is we've got a resistor coming down right there, and it could be any two resistors. In fact, it could be the two resistors inside the potentiometer. Okay, there's only one resistor really inside the potentiometer. We've got that one connection right in the middle of it. Let me give the screen something to focus on here. I think that's focused now. It tries so hard to stay focused. You can probably relate. And then we've got a resistor right here, and the symbol for this is light falling on the resistor right there, and that's coming down to ground. And at this point, we've got voltage going back to our Arduino. Now, if I'm at 5 volts right here and ground over here, well, just as a potentiometer went from 5 volts on one side to ground on the other side, this does the same thing, except we're always fixed to this point right here. What's changing isn't our position on a slide or anything like that. We're not physically moving something on a disk. We're changing the resistance of this connection right in here and making it either more resistive or less resistive. So we can lower that resistance down by putting light on it, or increase that resistance by making it dark. And if we increase that resistance, that makes this point electrically further away from ground, meaning that the voltage comes up. But if we apply light to it, that makes it come electrically closer to ground, meaning that this voltage comes down, and our Arduino pin reads a lower number. We can also change that by changing the value of this resistor right here. So if we've got a 1K resistor up here, then this is fairly close to +5 most of the time, so we'll tend to get higher readings. But if we put a 10K resistor in here, then this is a little further away, and we'll tend to get lower readings. So the combination of the two resistor values is what controls the voltage going to the Arduino pin, which controls the value that the Arduino reads. Okay, pardon me, that's usually a sign that I've spoken enough, and it's time to let you do a little bit of playing. One last thing to take a look at before we get to there. All right, so we've got this coming in right here. We're able to read pin A1. Now, what we're going to do right here is I'm going to add an if statement in here. So I'm going to get this out of the way. We're reading that A0 number. And tell you what, let's come in here. and we're going to bring in a control statement. And we used an if statement earlier, okay? And in fact, we used an if then else statement. It is not the COVID. Um, so we're going to come in here and we're going to do a little bit of math because we've got those pointy ends on there. And in here we can do a comparison. So I'm going to bring a comparison operator in right here. And I'm going to come and I'm going to grab my input and I'm going to read the analog pin on A1. And then I am going to read the analog pin on A0. Now, I'm just trying to see how I can refocus that. So there we go. Oh, you stay in there. You stay there. There we go. That's what I want. Sorry about shrinking it down there. I hope that's still legible. If not, you can read what's going on over on this side of the screen too, because the text always works, and that's what you can transfer to your real big bad breadboard board to do for real. So now it's going to go read analog pin A1, which is our potentiometer. And if the potentiometer value is less than the light dependent resistor's value, then let's turn on the LED hooked up to pin 10. So we'll say set pin 10 to high. And if it's not, set pin 10 to low and turn off the LED. So now we can start the simulation. Okay, and let's see what happens if we get light coming along. Oh, our threshold value needs to be changed a little bit. Just going to stop that simulation. And why is this sitting? There we go. Start that simulation again. I couldn't get at my potentiometer on there. Sometimes you have to come around and move things around a little bit. There we go. So let's bring the potentiometer up. Oh, as we change that potentiometer, we found a threshold value. And now, as the light level comes up, the LED turns off. So what this is letting us do is this is letting us use the potentiometer to set a value to compare something to. And now when the light comes on, we can control the LED. Now this is a bit backwards. Generally, when things get brighter out, you want the LED to turn off. So let's just stop our simulation and go back and change our code. So, and you could change this to greater than in here. Okay, that's one way to do it. Or you could have changed this to low and this to high. There's all sorts of ways that you can tweak your code to make it work. But now if we turn on our simulation, our LED is on. Still turning off when it gets dark. If analog read A1 is high, oh, maybe I didn't change it. I thought I did. Let's try changing it this way. Reverse the actions right in here. Okay, now it's dark and the light is on. Bring that up and the light goes off, and you can adjust your threshold value on your potentiometer so that at some specific light value, when it gets dark enough, that LED comes on. Now, the cool thing is that although we just did that in TinkerCAD, you've got all the stuff in order to do that for real at home on your breadboard. Okay, so you can hook your breadboard up, and you can see right here, I've put a switch in here, and we can use the switch to control an LED right here. There I've got a pull-up resistor, but as you'll recall, you don't need to use a pull-up resistor if you use the input pull-up command. So you can hook up your Arduino so you can use this switch to turn an LED on. You can use your potentiometer to control the brightness of an LED, and you can use the potentiometer in combination with your photoresistor to control when an LED comes on. So you can set something to come on when it's dark and turn off when it gets bright. And you can control whether something's dark or bright by coming down and putting your fingers over top of it, or coming along with your cell phone and using the little flashlight function and blasting your flashlight right in there. Yeah, it's so bright, it's so bright. Okay, um, something to play around with. You don't have an assignment to hand into me for this class this week because I want to take a little bit of time to make sure that everybody's got your LCD screens up and running nicely. If you've got all this up and running, why not try printing some of the data to your LCD screen instead of printing it to the serial monitor? I mean, print it to the serial monitor too. That's a good thing to do. You're starting to develop a little bit of a repertoire of code so you can start figuring some of these problems out on your own. Okay, well, that's today's lesson, and have some fun trying that out. Try it on TinkerCAD. If you like the drag and drop, do it in the drag and drop interface. I'm still using it where it works because I know a lot of people do like the drag and drop interface, but we're not going to be able to stick with that forever. It's not that advanced. When you've got code that's working in TinkerCAD, copy that code right into your Arduino IDE. Okay, you can copy and paste right into the Arduino IDE, and then remember your Arduino IDE before you go to upload your code to make sure that you're on the correct serial port. Right now I'm not showing any COM ports because I'm not plugged in to the board. When I plug in like that, it figures out that I'm hooked up on COM3. Sometimes you'll have other ones working. Hello world, and goodbye, and good night.